Okay, welcome everybody from wherever in the world you are, and whichever time zone you are in. My name is John Pugh. I'm the Technical Director for Photonic Integrated Circuits and Quantum Technologies at Optica. This is a special industry tutorial hosted by Optica Industry. Our mission is to provide value for our corporate members in the sense of connecting them with potential partners, suppliers, customers, investors, and talent. Today, we have more than 900 people registered to understand how we can help one of the success stories in silicon nitride production of photonic integrated circuits. We have one of the co-founders and chief commercial officer of Ligentec, Michael Geiselmann, who will discuss how they're able to integrate active components in their low-loss photonic integrated circuits. Please do use the chat function for Q&A or the Q&A function as well during the presentation, and we'll get to that at the end of Michael's talk. So without further ado, I give the floor and attention of everyone to Michael Geiselmann.
Thank you very much for the introduction, and thanks for hosting the webinar. Today I will discuss the low-loss platform and how to integrate active components in the low-loss platform. So probably everybody is aware that in electronics it took tens of years and many dollars to integrate from bulk components into what we have now, millions of transistors per square millimeter. And in photonics we see the same trends, and we want to repeat the success of the electronic chip revolution and revolutionize the optics, where we integrate a lot of optical elements that are up to now in bulk onto a photonic integrated circuit. And here to the left you see an experiment from a Chinese university that did an experiment on an optical table with bulk optical components for a quantum computing experiment. And on the right you see a chip that is from Xanadu, a quantum company in Canada that fabricates chips that uses chips fabricated by silicon nitride. Ligentec's mission is to serve both markets that has very high value add to the application by choosing photonic integrated circuits, but also very high volume applications by going to miniaturization. And our mission is to unleash the potential of photonic integrated circuits, or in short, let's PIC it. We are a European PIC company with a global reach. We have our headquarters in Lausanne in Switzerland. We have an entity in Corbeil, which is close to Paris in France. And the beginning of the year, we also opened the entity of Ligentec Belgium, located in Ghent. We are a bit more than 70 photonic enthusiasts driving the business, and from design to fabrication of photonic integrated circuits that have a global reach. And we provide best-in-class integrated passive silicon nitride photonic integrated circuits with very low loss numbers, below 5 dB per meter for a single mode, and below 1 dB per meter for multimode waveguides, and offer that in 3 different platforms that I will describe, with an extensive PDK. And we're also ISO 9001 certified to accompany all the business processes from first customer interaction to delivery. And our journey, as our customer journey, as we see it, is from entry of R&D and prototyping, where we offer an open access, low barrier to our multi-project wafer runs using an established technology with a fixed layer stack and an extensive PDK, which is offered in regular multi-project wafer runs. We run those approximately every 2 months. This can be seen on our website. And also custom runs, dedicated runs. And here we support customers with design and layout, characterization, and packaging. We also take on engineering studies and layer stack adaptations and custom integrations for custom PIC developments, and give customers access to early technology developments, which I will discuss further in the presentation. In the end, as I said, our mission is to unleash the potential of photonic integrated circuits and to bring those into a product where we can make a difference. So we want our customers to succeed and go to pilot and volume production. And here we have a strategic partnership with X-FAB, where we installed our photonic process, and we can deliver pilot and niche quantities, but also high volume quantities in a high capacity wafer fab with fully automated testing and an automotive quality system. Our customers come from different fields, and we see that our technology is an enabler for advanced computing, which we also include quantum computing, neuromorphic and optical computing, that is now very much in trend for also artificial intelligence. The communication, what we understand about not only normal telecom networks, but also QKD, any kind of data transmission and satellite communication, and sensing that ranges from OCT or LiDAR up to quantum sensing, biosensing, fiber sensing, and metrology. So probably for those who don't know yet, I assume that everybody does, but for those who does not yet, the benefits of silicon nitride is a very large transparency window. You see that already from the applications from 400 nanometers up to the mid-infrared. You can get very low propagation losses in that technology, and you can propagate a lot of optical power through the waveguides. We measured 5 watt in a waveguides, which is like 10 to the 9 watt per square centimeter. And that always in reference to silicon, and I don't want to do here a direct comparison. This is just an order of magnitude higher than orders of magnitude higher than in silicon, and order of magnitudes lower loss than in silicon. And the beauty of that material, that it's scalable to volume. It's a non-toxic material, so we have that installed in a high volume CMOS fab, and that is benefiting customers not only in the areas of telecom and datacom as we have them as the markets as of today, but required for many other applications that I already mentioned. So why are low loss important for sensing? We have applications such as FMCW LiDAR, where laser chirp control needs long delay lines, and the more delay you want or you need, the higher the losses. And so if you have a low loss platform, you can have low loss delay lines. Also for narrow line width extended cavity lasers, the low loss of the silicon nitride enables a narrow line width of a laser that it's attached. And phase noise is always related to losses. In terms of communication, if we look at the use case of MAX or DMAX, and IWG again is always the phase noise related to losses, and ring resonators, the higher the quality factor, so the lower the loss, the narrow the bandwidth, the narrow line width filters you can achieve. And in communication also you can do tunable narrow line width lasers with that technology. And in computing, as I already mentioned, quantum computing or optical computing, you can use nitride for photon pair generation and photon processing. And for that, you need high Q ring resonators, access to also nonlinear optics, but also very low losses in propagation and Mach-10 interferometers. So we want to unleash the potential of photonic integrated circuits. We want to pick it, and we have two paths to pick it, to put the photonic integrated circuits into products. One is that we have the best low loss platform, and we integrate the light modulation and detection on the photonic integrated circuits on top of the silicon nitride, which has the lowest loss. So let's start with the low loss passive photonic integrated circuits that we can fabricate at scale in volume. Here we have three standard thicknesses: 800 nanometer, 350 nanometer, and 150 nanometer of silicon nitride. And we have a bit more than 10 process modules. And what we consider as a process module is every modification to a waveguide. So we have different thicknesses. We can stack several levels of waveguides. We can do RIP in a waveguide. We can do a cladding opening in a waveguide to give access to the evanescent field, and we can integrate heaters to the platform to change the effective refractive index of these silicon nitride waveguides. And that goes in combination with an extensive PDK, where we have standard components, and that PDK is available in the standard software houses for design, simulation, and layouting. And each of these thicknesses, they have certain key performances and key areas where they're employed with. So the 800 nanometer thickness has a very high mode confinement. So more than 90% of the mode is in the waveguide. We can get quite low loss with a single mode waveguide at 1550 nanometer. And we can provide very small bend radius that goes down to tens of micrometer, and have access to dispersion engineering in that by changing the width of the waveguide. The PDK is available for C-band, where we have an extensive component library in C-band, including below 1 dB facet edge couplers, but you can also design components in O and L band, and even further, as I show afterwards. So here an example to the right of a circuit of AWGs that was used for a spectrograph. So you can put your design in a very compact here 2x7 millimeter chip. Another use case of that platform is to generate frequency comms or benefit of nonlinear phenomena of the silicon nitride. If you have your appropriate dispersion engineering, you can generate supercontinuum or frequency comms that span everything from a few lines up to an octave of comm span. And as you have a very high mode confinement for the C band, you can even go higher in wavelength and also propagate wavelengths in the regions of 2.5 micron, which has been shown in this work where a laser was attached to a silicon nitride circuit, and where they could tune the laser and narrow the line width even at 2.5 micron of wavelength. The AN350 nanometer platform has very good loss performances in a single mode waveguide down to 5 dB per meter. In a multimode waveguide, even below 1 dB per meter at 1550 nanometer wavelength. And usual wavelength ranges that are addressed with this platform are O-band and C-band, and some of the applications even go down to the near infrared. Here again, we have facet edge couplers for below 1 dB per facet, and a PDK for C and O band. And here an example of having long spirals or long delays, then in combination with other process modules. But if you want to have a long spiral or a long delay, then that could be a very good option to get very low loss spirals. And in this case, what was done in addition, this is from a European project. We deposited a gain material on top to get an gain on the chip to do a pulsed laser. And then the third standard thickness is 150 nanometer, where we address visible and near infrared applications. We also have cladding opening for sensing, or some of our customers also want to use it for very low confinement in the IR wavelength range. And here's an example of a beam combiner in the visible wavelength range, which is in bulk optics. And here with that platform, we can do beam combiners on chip in the visible wavelength range. And I mentioned cladding openings for sensing. So usual scenario is that you have a Mach-10 interferometer where one arm is exposed to the to air, or where then you put your gas, your liquid, or any other material what you want to sense. And then the waveguide interacts here with gas or liquids that you want to sense, and then gives you a signal of that substance that you want to test. And there's a few companies that are looking into that, and in the realm of Photonics Fab, which is a European consortium to industrialize photonic integrated circuits. Aribal is developing a photonic sensor to have an electronic nose. Some of our PDK components here, a few highlights. We have a compact low loss crossings that has been shown together with simulations of ANSYS. So a first time fabrication. Here we have a comparison between simulation and measurement of that first time fabricated circuits. We have simulated 0.016 dB of excess loss and measured 0.017 and the crosstalk below minus 60. And so you see in TE and TM simulation and experiment match quite well, which means that we have a quite good understanding of our platform and our PDK, that people can even put their own components that and have a first time write possible. A new process module that we have introduced in the beginning of the year is undercut module, where we address the monolithic integration of modulators in the kilohertz range. And here we do we take away the silicon from underneath the waveguide. So you have a better isolation. And the red one here, that's the heater. The purple one, that's the silicon nitride. And here that is then air, what we then call an undercut of the process. And this monolithic undercut heater on top of the standard silicon nitride process gives high phase shift powers of 10 to 15 milliwatts and speeds of a few kilohertz. Also a module that is very very well asked for is the high performance optical I/O, where we have a proven track record in development of efficient optical I/O interfaces, where we here with this module we enlarge the mode field diameter on the chip to match an SMF28 mode field diameter of a fiber at 1550 nanometer wavelength. And when we scan around the wavelength here on a package device, so we couple a fiber to the chip, have a loop, and go back to the fiber, we get less than 2 dB in total coupling loss, fiber chip to fiber, with this standard with this module and the standard SMF28 fiber. In order to even more standardize, we also lower the entry barrier for packaging. This is more on the prototype level, to have an effective demonstrator or chip verification without the need of an optical bench, where we have templates of circuits that matches with a packaging provider, and where we have easy to design and package modules that we are offering. So this was just an overview of what we can do in lowest loss passive photonic integrated circuits at scale. And the next few slides I will talk about how we get light modulation and detection on the photonic integrated circuits here. And our view is that we want to maximally leverage the mature silicon nitride platform, and to keep the post processing as simple as possible and in the back end of line. And so we take a 200 millimeter silicon nitride wafer with all the standard modules that you see here. So here a standard module, as I mentioned before, is a cladding opening where you remove the oxide and you get access to the evanescent field of the silicon nitride here below, and then you can integrate heterogeneously other materials to it. And so one integration is what is shown here, is the integration of photodetectors that we're doing with component transfer printing for complex active devices, where we collaborate with established suppliers for 3.5 lasers or photodetectors. And in other approaches, we we do layer transfers like bonding when the device fabrication is simple and can be done post front end and at wafer level. For example, our hybrid mode thin film lithium niobate silicon nitride modulators that I will introduce in a few minutes. So we have modulation, detection, and lasers that we want to integrate in this very low loss silicon nitride platform. And the modulation, we take the silicon nitride 200 millimeter wafer, we bond a lithium niobate wafer to it and structure it to get in the end lithium niobate on silicon nitride integrated to a low loss RF modulation, and to have the thin film lithium niobate on silicon modulators on a wafer scale process. So how we do that is we have the advanced silicon nitride platform with a full PDK, which is here on the left-hand side, and here we combine then that with by integrating thin film lithium niobate layer for the modulation, and that hybrid mode is the heart of the modulation to get access to the properties of the thin film lithium niobate, whereas the mode is still guided with the silicon nitride, but has the properties, but is mainly located in the thin film to get access to modulation of the light. The patterning is done in silicon nitride, and the thin film lithium niobate is just a layer. And the essential components are only in the thin film lithium niobate, which is the modulator. All the other components remain in silicon nitride. And this is what we get in first runs. We have bandwidth that is exceeding 10 gigahertz, 3 dB bandwidth, with VPILs reaching down to 3 volt centimeters, depending which wavelength, and end-to-end fiber-to-fiber loss of less than 4 dB, which will be much lower in the future. So this is only the start. So we will get the fiber-to-fiber loss of such a modulator device much lower than this 4 dB. And the big advantage, apart from the very low loss, is the compatibility of the PDK, that we have high Q ring resonators, very low edge couplers, and all standard building blocks available in that platform. In terms of detection, we, as already mentioned, we're doing transfer printing for flexible photodetector integration And for those who are not familiar with this technique, is that you have a source wafer with 3 fabricated photodetectors, and you take these photodetectors with a stamp and put them on a silicon nitride target wafer. That in the end you have your silicon nitride circuit, and your photodetectors put there with a microtransfer printing technique where needed. In our first fabrications cycles, we did that with InGaAs photodetectors, where we like as described, we fabricated 200 millimeter silicon nitride wafer, open here that oxide window to get access to the evanescent field, and then place the photodetector in that opening and do the contacts here. So here you see a fabricated device. The photodetectors are super tiny. This is the waveguide here that then evanescently couples the lights to the photodetectors, and you have the contacts to do the readout of the photodetector. And that is very useful for applications where you need many photodetectors in one chip. And here's one example that you have an error waveguide grating. So you want to split from one channel the light into many different channels, and here we come in with one channel. We put the light of different wavelengths into one channel, go through the error waveguide grating, split the light up into different channels, and detect it then here with microtransfer printed photodetectors, and can get a readout of that AWG directly on a silicon nitride chip. And here we partnered with X-FAB, that is already our strategic fabrication partner for the silicon nitride, and Accelerprint to form the world's first integrated value chain platform initiative for heterogeneous integration in photonics, whereas Ligentec has the know-how of the silicon nitride technology and doing the transfer printing, and the Accelerprint has the know-how of the transfer printing, and X-FAB has the know-how of scaling that to volume. The last piece is integration of lasers. There's many different schemes how to integrate lasers, but what we can offer as of today is lasers that can be integrated in what we call a hybrid integration, where in comparison to what we call heterogeneous integration for the other techniques, or monolithic integrations. So here you butt couple a laser to a silicon nitride circuit. In this case, you have a reflective SOA that you butt couple to a silicon nitride circuit with components. Here you have a spot size converter that is adapted to the mode field of the laser. You have a phase shifter that contains a heater to change the effective refractive index of the silicon nitride waveguide, and then you have a Vernier filter with these rings that are again tunable. And here we can then in the end fabricate a chip that narrows the line width of a 3.5 laser, which is usually hundreds of kilohertz, to a line width that is below below 3 kilohertz in that case, and probably even sometimes reaching below kilohertz line width. Still with a lot of power in the waveguide, in the laser, and the emission, and large tunability due to the heater that are integrated on top of the silicon nitride waveguide. And the beauty of that is that this was an example for 1550 nanometer, but you can also do the same for other wavelength regions. And here there are two papers that did that on our platform in around 2 micrometer wavelength region and around 2.5 micron wavelength region, where the same concept applies. You have your laser that is butt coupled to the low loss silicon nitride waveguide with integrated heaters, and you use the same physical effects to narrow the line width of your laser, and can so do that in different wavelength regions. And this is not only possible to go to higher wavelength regions, this is also possible to go to lower wavelength regions, then depending choosing a different platform of our standard platforms, 150 or 350 nanometers, whereas this work was done at 800 nanometer platform. So that is the unleashing potential of photonic integrated circuits, to put photonic integrated circuits into products. So we want to pick the products, and that we do with this very low loss passive platform, where we have multi-project wafer runs every 2 months, and also offer dedicated runs that can be run anytime. And we're working on integrating modulation and detection on the photonic integrated circuits. So on these passive circuits that are fabricated in a volume fab, we are integrating light modulation and detection, and that we also offer through Ligentec Labs. And just to explain what Ligentec Labs is, so we provide early stage access to advanced technologies, and the idea is to have that from the lab for the lab in a early access cost sharing mode. And for the customer, there is the opportunity to steer the technology development from the application, and we have offer this also as multi-project wafer runs now, and there is an upcoming run in January for modulation and for the detectors. With that, I would like to thank you for listening, and I'm happy to answer questions in a discussion.
Excellent. Thank you, Michael, for a great talk once again. So we have obviously a few questions in the chat. There's been some conversations going on in the background, but it's only fair to give you a chance to answer too. So Jonas was asking, will the waveguide be multi-mode at 800 nanometer thickness?
No, so no, no is the short answer. So you have it depends on you have the flexibility on putting your defining the width of your waveguide. So you can design a waveguide that is 800 by 1 micron, and then you have a single mode waveguide. You can also design a waveguide that is much wider. Then in principle it can have multi-modes, but you can still put taper sections in the waveguide to ensure that you only allow in the multi-mode waveguide a single mode propagation.
Great. So Shankar is asking, what is the propagation loss in the visible range?
In the visible range, again, visible is very broad. So visible ranges covers 400, 500 nanometers, depending to who you talk to. We get propagation losses in the red of about 0.2, 0.3 dB per centimeter, and it gets a bit higher if you go to the blue.
Great. There's a couple of questions around the heaters. What software do you use to model your heater behavior?
So in the PDK, all the heater material constants are in the PDK, and how you can model it is, for example, with ANSYS numerical to have in that software to have to use our PDK and model the effect on the optical waveguide of the heater material.
Great. And what modulation solutions, was it heaters or Tiflin, are available at visible wavelengths?
So at visible wavelengths, the heaters are available. So all the passive components or modules are available in the near infrared as well as in the infrared and visible. So you can have access to heaters also in the visible wavelength region. At the moment, the focus for the lithium niobate is on O band and C band, but intrinsically there's no problem to also integrate the lithium niobate for the visible wavelength region, but this is something that needs to be discussed with the customer.
Right. And Jorn is asking, what is the relaxation time for the undercut heaters?
So you have I don't have from the top of my head the relaxation time, but what happens if you have the if you have the undercut heaters is that your speed drops and you get and you get some kilohertz that you can modulate your signal with.
Right. Just jumping back a little, so you mentioned the high power 5 watt in the waveguides. What thickness was that quoted for?
That was quoted for 800 nanometer, but intrinsically, so silicon nitride does not have any problem of having to photon absorption that for example happens in silicon. So the 5 watts in a waveguide was in the 800 nanometer waveguide, which means that the power density in the waveguide was extremely high. If you go to a thinner waveguide platform, the power density is relaxed because the mode is getting bigger and the power is in a bigger area of the mode.
Great. And it's quite a related question. So Ali is asking, so for quantum photonics applications, do you mean the silicon nitride is used for the generation of single photon emitters due to nitrogen vacancies, or is it the case the it's the transmission through the silicon nitride that generates the photons?
So I'm not sure, like the NV centers, they generate the single photons in a case where we can generate single photons is in a scenario that you have for example at here, but that's probably better shown here, where you have you come in with a light, distribute your pump source, and then you have your ring resonators, high Q ring resonators, to get squeezed states, and this is very similar then to or the intrinsic processes are similar to frequency comp generation. So here you can then you can generate single photons in these ring resonators, and this is mainly done in above 1 micron. I'm not sure if someone already has demonstrated that also for wavelength regions that are used for NV centers like 637 nanometers.
Great. So York is asking, how much additional space is required on the chip for enlarging the mode field diameter from the 1 micron to the 9 microns at the edge coupler? Roughly, I guess.
Yeah, roughly hundreds of micron.
So it's quite large, and obviously this would be smaller if you're only required to go up to 3 microns, for example. Yeah. So there's another question here from Shankar. What is the 1 dB bandwidth of the fiber to fiber coupler? If that's, I think that was a question from early on.
1 dB bandwidth of the fiber to fiber coupler. In terms of, I'm not sure if I understand the question. The bandwidth of like a fiber to fiber coupler in terms of wavelength, or yeah, I'm not sure if I understand.
Yeah, good point. Okay, so we'll move on from that one. So integrating thin film lithium niobate on silicon nitride is a valuable achievement. So what are the prospects of incorporating polymer or BTO? Is this something Ligentec is looking into?
So there's no intrinsic hindering points to integrate other materials. BTO is very similar to would be very similar to lithium niobate. It's a material that comes on a wafer, whereas a polymer needs to be integrated with, so it's a liquid, or yeah, you spin it, spin coat it on it. So it's a different type of integration that we don't have the expertise of neither polymers or BTO. So here we need to work with providers of that to integrate that.
Great. There's a question from Sarad asking about offering the fabrication of inverse design devices. So I guess this is asking what the minimum fabricatable feature sizes are.
Yeah, so in inverse design is possible, but yeah, like you said, John, it depends on how small these feature sizes are, and so we cannot do like 10 nanometer feature sizes. That's also like we use stepper lithography and are bound to the feature sizes by stepper lithography and not e-beam.
Great. Jan Philip is asking, will you further focus on transfer printing for the integration of actives?
So that is one route. The integration of lasers, that is very important for many applications, and transfer printing is definitely a path that we're looking into, especially as the 3.5s of the photodetectors as we already integrate them.
Great. There's a question from Marius. Do you have a polarization beam splitter rotator in the PDK?
Yeah, yes, we do. So we have polarization we have polarization components in the PDK, and here, yeah, you feel free to contact us to get more details on that.
Excellent. And on the PDK, is it possible for users to contribute to the Ligentec PDKs if they, for example, find an sort of exotic design for a good coupling on
Yeah,
a
I put it in a different way. So customers are free to use their own structures, that they don't if someone believes that they need a new structure, we're open to that if that doesn't infringe our manufacturing and design rules. Everybody can put their own structures. And then what is a PDK? A PDK is not just a design that is fabricated once. A PDK is a design that is fabricated over and over again. And you need in the end to get the statistics of that design. So there, then that we need to test and fabricate many times and test many times a design that we can then offer it afterwards to other customers in the form of a PDK that has a certain statistical probability to achieve certain performances.
Right. A question from Luis. So what about acousto-optic modulators? Are there possibilities to integrate with a laser, for example?
there's always a possibility. So it has been shown scientifically that this is possible. It just requires a lot of effort and time and money to do so.
Great. So there's a question here from Adrian. Can you do Mach-Zehnder interferometers at 1 micron? And what would be the losses to inject from an SOA and from Mach-Zehnder interferometer to photodetectors?
So yes, we can do Mach-Zehnder interferometers at 1 micron, and values. I don't want to comment too much about this is the exact value, because it depends a lot on the mode field diameter of your SOA. What's the indium phosphide or whatever other platform you're having has as to mode match. But silicon nitride is a very good platform to mode match to other platforms, and a value of 1 dB is not out of question, or below 1 dB, if you can match the mode field of the SOA.
Great. And I'm just going to ask one final one. Have you achieved high-speed photodetectors over 10 gigahertz at 800 nanometers? And what would be the losses from the waveguides to the photodetectors?
So losses from the waveguide to the photodetectors are minimal. Doing evanescent coupling. We have not looked at the 800 nanometer of wavelength for photodetectors. The photodetectors we have at the moment are in C-band, but intrinsically I don't see an issue to go above 10 gigahertz. That depends then on the material of the photodetector. So we would use similar techniques to integrate those photodetectors in our passive platform.
Great. And just one final question, as it's asking where to find something. Where can Anchor find more information on the upcoming MPW runs with the Tiflin modulators and photodiodes?
So we have on our website we have information about the MPWs, and there's also links to get in contact with us. Just send us an email and at info@ligentec.com, and we can then share more information about these upcoming MPWs.
Great. Thank you, Michael. So that brings us to the end of this webinar. So please do get in touch with Michael and Ligentec to ask many more questions. Thank you for the great talk. And I'm looking forward to seeing you next week to present at the Optica Quantum Industry Summit in Bristol. Thank you, Michael, and thank you everybody for taking part. Bye.